Guys, we're going to get the party started, okay? So enjoy your meals. That's fine, but enjoy it by shutting up. Oh, else to sugarcoat it. Are you ready? So continuing, we talk a little bit about, number of cylinders and the layout, and you guys got to understand a lot of this has to do with what they want the engine to do. For example, back in the day, Chevy had a V8, and then when the fuel economy crisis hit and emissions and the oil price and all that, they decided to make a V6. So how did they design the V6? They cut the two back cylinders off of the V8. And it had a vibration because it wasn't really designed from the ground up. But they didn't have the time to design it from the ground up because the gas prices blew up overnight. So they cut the two back cylinders off, started punching out V6s, but with the vibration, they're having potential issues like this. So they actually added a balance shaft, and the balance shaft kept the engine in balance so it didn't vibrate itself to death like this, right? So as we get a little bit further in, we talk about balance shafts and stuff. That should be one of the reasons we'd use one. All right, so when we get into the number of cylinders, it also affects the sound. That's a big one to me. So anybody like the sound of a V6? For me, there's a couple problems with the Ford Raptor. The first one, I just said it, Ford. The second one is those Raptors are pretty quick actually, but when they accelerate, it's just kind of like, bah. I'm like, no, I can't do that. Now the Raptor R sounds pretty good. You know why? It's a V8. The V8, for some reason, the V8 has that frequency is just a lot more appealing to me. But some people like the V6. Some people like the 4. If you get into motorcycles, 4 cylinders are pretty common. But like a Honda or a Suzuki, for example, is a flat plane 4-cylinder. And then you have Yamaha, which is a cross plane 4-cylinder. They sound entirely different. Cool. So just pin that in your mind, as I'm going to give an assignment later talking about how the number of cylinders and the firing order, all that stuff affects the frequency of the engine. And for me, I'm a little, it needs to sound good or I'm not interested. Basically, that's what I'm telling you. Right? But you can look into the science of all that too. There's a dude who does music, and he actually did a computer program that makes a little sound at a certain frequency in time, and it replicates the sounds of the engine, and you can tell why they sound the way they do. It's pretty cool. All right, so we get in there a little bit more. We talked a little about the engine configuration. It's mostly how the cylinders are arranged. So if you look like this next slide, what the heck is that thing? That's an inline, right? But it's slant. So like if that was an inline 6-cylinder at a slant, old cars, they'd call that a slant 6. So when we're talking about the engine, a lot of times it has to do with how the cylinder is arranged and how many there are. Okay. So inline, all in order, one bank. It only has one bank, right? Opposed, pistons are in 2 banks. So like this, they're opposed, right? This one is opposed to this one. What might we call this as a slang term? A boxer. So there's your boxer, Subaru and Porsche, which is really pronounced Porsche, but I still say it Porsche, even though it's wrong. Okay, you got V. V is more like the V6, V8. If you have a 4-cylinder engine, you think it's a V4? It's probably an inline 4, but my motorcycle is a V4. So people will ask me like, man, what is that engine? I'm like, it's a V4. And they said, well, I don't think it's a V4. You mean it's a 4-cylinder? And I said, no, it's a V4. And they look at me weird. It's got 2 front cylinders and 2 rear cylinders. So if you look at it like this, it's literally a V4. So there are V4s, but not very commonly. Like a couple motorcycles have them. That's about it. Then you get a little bit more advanced, VRs and Ws. It's like if it's a W, yeah, something really high end. Picture a V8, except they actually offset the cylinders even within the bank. So if you were to take a V8, flip it to the side and be looking at the cylinders, You'd have one high, one low, one high, one low. And that's kind of like the shape of a W, right? At least starts to make a W. So you get into, there's some other less common, abnormal things. Honda, for example, made an oval 4-cylinder. It was the pistons are like this. They're literal ovals, right? So there's some weird stuff out there, but mostly inline, opposed, and V. That's mostly what we're going to be seeing. Okay. Now this one, who thinks they know why it's tilted? Why is it on a slant? Wasn't balanced. That's a good guess, though. It's a good guess, though. That's exactly it. But why does that matter?
Better.
True, and we want a low center of gravity. We want a low hood line. So, like for example, people are always giving a hard time to the generous motors, government motors, whatever you'd like to call them, about the Corvette. The Corvette is still a push rod engine. That means cam and block. It's not overhead cam. So they'll be like, oh, GM is still using stuff from the 70s and 80s. Ford's gone to a dual overhead cam. Well, think about that. If you have the cams up high, that makes the engine taller. You ever seen the hood line on a Corvette, like a C7? They're low, low, low. So they're trying to keep everything low. That's one of the main reasons that GM didn't jump all over the dual overhead cam V8. They do have some dual overhead cam V8s. They're not real common. One was in the old ZR1. It was made in partnership with, I can't actually remember, some more exotic race company designed a dual overhead cam V8 with them. It wasn't Yamaha, I don't think. It was man, I can't think of who it was, but some high-end company. It's not that they can't, it's that a lot of times the engineers are looking at where is this engine going to go? What is it going to fit into? What shape can it be, right? That's why they slanted this one. Cool. So if it's, let's say, an inline 4, inline 6, they do have actually inline 8 cylinders. Way back in the day, old cars, 8 cylinders right in a line. But not real common. You got the V's, so V8's most common, V6, V4. There are also V10. Anybody seen the V10 in anything? Viper, truck, exactly. Ford puts the V10s in excursions, bigger F like 250, 350, and sometimes even the vans, and sometimes in motorhomes. So V10 is not actually that abnormal, the Triton V10. And they do have some V12s, and they do have V16s from way back in the day, or on locomotives too. And then they got flat, and a lot of times when they say flat, they're talking about opposed, right? So if someone from Porsche, I just can't say it, Porsche is going to say like, oh, I have a flat 6. And you're like, flat. You know what that means? Opposed. 3 cylinders and 3 cylinders. That's your flat 6. Again, that's kind of nice for racing, right? Low center of gravity. When you get up higher, that's when it tends to get a little more body roll on turns. Daniel, go ahead. 6th gen. What year is that? Robbins?
No.
Oh yeah, I remember those. But it's in their front. I don't think that's actually a slant. I think that's a regular 4-cylinder, but they index the whole engine back to get the hood line lower. I've seen those. Those are the ones where the exhaust is kind of coming out at you like this. Yeah, I remember that. This one I'd like to point out. If you look at this one, it's not just that the engine's thrown in there sideways. It's that the oil pan starts out vertical and then it's tilted. So that's why this one's a slant. This engine's actually slanted. It's not a regular 4-cylinder bolted up at an angle like the Celicas, but I do remember those. Yeah, those were good. And then we start talking about between the banks, especially when we get into these weird ones. Like let's say you could have 180, that's opposed. Or you could have a 90, that would be like a perfect right angle. That would be a V. So if you stood that up and you looked at it, that would be a V6 that's at a 90. The problem with those is they do tend to get a little bit wide. So sometimes they'll make it a little bit less. Like you might do like maybe a 60. And then if it's a true like a VR, that's almost an inline, but technically those cylinders are they're off by like about, I don't know, 15 degrees, right? So it's not really a V, it's not really inline, it's a VR. It's just the way it is. Kind of similar with the W, right? So they'll offset them a little bit. Why do they do it? Depends on the number of cylinders. So like if you're really trying to pack cylinders in a smaller space, you know, if you just think about it like this, if I draw a circle like this, and you measure that distance, then what if I were to draw a circle like this and then sneak one a little lower and you measure that distance? You could actually fit more if you start to offset them. See? So that's when they start to get into the W's and the VRs. It's really just to make room. That marker's kind of trash. I won't use that one. That one's nice. And then sometimes they're doing it for some other reasons, but those are the common ones. It's always trying to get the engines to fit inside of the particular vehicle. Cool. So there's your opposed. Subaru, for example. Here's a pretty narrow angle V6. Like if you look at those two cylinders and you draw a line, that is definitely not a 90. That's probably like a 60-degree V6. So if you were to read some of the magazines on the engine spec, they'll be like a 60-degree V6. And you're like, 60-degree what? They're actually talking about the offset of the angles, the difference between the two. Cool. And then generally when we get into rotation, if you were to walk up to the engine, almost all the time, I did bring this over, almost all the time, if you roll up to the engine, the crankshaft is going to turn this way. Let me screen flip. Here we go. Oh, I wasn't sharing right. I am fired. Okay, so you guys on Zoom, you see this, right? All right, good. So when you guys are looking at this, you can see this is going to turn clockwise from your perspective. That's the norm. Make sense? So normally if I go up to an engine, I'm going to work on it. I'm looking at it in service mode like this. This is the way you do it. Now, technically, the way that the engineers will describe it is they'll say, you get up on the engine like this, and it turns counterclockwise. And that's how they look at it. It is kind of weird. For some reason, they always want to go, yeah, and jump up on the bell housing and look at the engine and be like, see, it goes this way. Same with like, this is the left side of the engine, right? Whereas if you walk up to it, you're going to think clockwise, cool. And you're going to say that this is the right side of the engine when in reality it's the left. It's just a perspective thing, okay? Now let me do screen share. You guys tell me if the right screen shows up for me, okay? Now you should see this. You should see the presentation. All right, good. Okay, so that's kind of what it's saying. And then when it's front wheel drive, it's generally the same, but it gets a little more complicated because there's no right and left, right? It's always a little bit of a weird thing to explain. And then this just gives a brief overview of Atkinson and Miller cycle. So generally, when we get into Atkinson and Miller cycle, you're talking about hybrid and efficiency, fuel economy, lower emissions, right? So we can kind of save that a little bit for the end, but just so you know, both of them are going to effectively shorten they're going to lessen the displacement by, let's say, if you're coming up on compression, we could bleed off a lot of that compression and then close the valve halfway up, and that's going to make the displacement half. That's kind of what's getting into. Again, it has a lot to do with fuel economy and emissions. The negative that you must know now is because we're holding that intake valve open so long, or the exhaust valve, whatever we're doing with the VVT, we're not going to make as much vacuum because we're trying to do an intake stroke. And during the intake stroke, you know, a lot of times what we'll do is we'll have the intake and the exhaust stroke open. We'll have them overlapping. So therefore, it doesn't really make a lot of vacuum. Now, if you zoom out for the whole car, like a holistic view, if your vacuum is supposed to normally be like 22 inches of mercury, but you do Atkinson or Miller cycle, and now you don't really make a lot of vacuum, what part could that affect? The brake booster, that's the big one. So on these vehicles, because they're Atkinson cycle or Miller cycle, which is a Atkinson with a supercharger, we don't have a very good vacuum source. So everything I'm about to tell you when we get into towards the end of class about 22 inches of mercury and stuff, that's for a standard regular engine. That all goes out the door when it's an Atkinson because we're playing around with VVT and we're not going to make 22 inches of mercury. We may make 11, and 11 is normal, but not good enough to run a brake booster. So what do you think they may need to do on the more modern 4-cylinder? Run a vacuum pump. Bingo. So if you see an Atkinson cycle, it's going to have a vacuum pump somewhere. A lot of times they'll put it right on the end of the head and the camshaft will turn it. And that vacuum pump serves the purpose of running any vacuum related accessories, mostly the brake booster. Make sense? If you go to do tests on the Atkinson cycle and you disconnect the brake booster and you measure the vacuum at the brake booster, are you measuring the engine's vacuum? Yes or no? No, why not? Because you're measuring the vacuum pump. And see, when we want to do a health check of the engine, we can check the vacuum, and the vacuum can give us an indication if the compression's low and if it's, if the cylinders are sealing well. Like if an engine doesn't make good compression, it won't make good vacuum. Make sense? So sometimes we'll do a vacuum test and be like, oh, the vacuum needle's bouncing or it's not reading very well or whatever. Then we know that there's a mechanical engine problem. Make sense? If your vacuum is low and your needle's bouncing, it's not because the cat is clogged. It's not because the spark plug is fouled or something. Like mechanical engine problems will result in like vacuum readings that are off. Cool? So you got to know what you're actually testing. On an Atkinson cycle, you have to find a spot where you're actually testing the intake manifold port vacuum, like the actual engine vacuum, not the vacuum pump vacuum. Okay, remember that. Cool. All right, overall pretty good. And then when we get into variable displacement engines, there's a lot of ways that this can go. So variable displacement, what do you think that means? Maybe it could be a 6-liter or a 3-liter. It can be a 6-liter that identifies as a 3-liter. No, like it goes actually back and forth. It can't be like, well, I have 6-liter V8 power, but I have 3-liter 4-cylinder fuel economy. Like they actually have to flip back and forth. So if you look, GM's one of the more common because it's been a kind of a failure. They have a V8. When you need the power, it's a V8. When you don't need the power, it shuts down 4 cylinders. It stops sending oil pressure to the lifters. The lifters collapse, and now you have the cam trying to open and close the valves, but the lifter's dead. It's like you guys remember we talked a little bit about this lifter. If the lifter's flat, the cam will be trying to go up and down, but the valve will just do nothing because the lifter's flat. So it won't open and close the valve, so therefore those cylinders won't work. It'll do that on 4 of the cylinders. So you have 4 cylinders doing nothing and 4 cylinders doing the work. So you have like a 4-cylinder. You have a V4 actually. 2 on one side and 2 on the other side. But then when you step on the gas and you need the power, boom, it'll send oil back to those lifters, and now you have your V8 again. So you have V8 when you're on the accelerating, and you have a 4-cylinder when you're cruising on the highway. Make sense? That's the goal. There's been a lot of other ways to do it. This one, for example, you can see it's going to either, this is like the GM one, it's going to send oil pressure to the lifter and activate it, or not send it, which won't activate it, but it's using the oil pump. So we need good oil pressure for this to work. And additionally, it's using a solenoid. This is a deactivation solenoid to either block the oil flow, which will allow the lifter to pump, or allow the oil flow, which will bleed the lifter off and deactivate it and no longer open the valves. Make sense? So what part is controlling the 4-cylinder and the 8-cylinder? Solenoid controls the oil. What controls the solenoid? Right. So when we take a good look at that, we're talking about the PCM controls the solenoid controls the oil flow, and the oil flow ultimately controls the lifter, and the lifter controls whether it's in 4-cylinder or 8-cylinder mode. So if we had a problem with this, it could be the PCM, it could be the harness, it could be the solenoid, it could be an oil pressure issue, it could be a lifter issue, right? So like you got to know the whole system when you get into these. The most common failure by far is the displacement on demand lifter. So you have a lifter on screen. This is a normal lifter. You can notice these look different. Like this one is going to be really small compared to that. They're very different size. Lifters are pretty simple, but when they're displacement on demand, there's a lot more going on right there. And these are failing somewhat regularly. And one of the reasons people are suspecting they're failing is, you know, they have really long oil change intervals, and you have your turning oil on, your turning oil off. And if you get, you know, some kind of clog in the passage, it's either going to be stuck in 4 or it's going to be stuck in 8, or at least that cylinder. So I've seen a couple of these where the lifter is permanently in 4-cylinder mode, and the vehicle's got a misfire. So what's kind of crazy is when you're in V8 mode, all the cylinders are working. Then when you're in 4-cylinder mode, only half the cylinders are working, but they tune it and they shut down a specified cylinders. You don't even really feel it. You can't tell if you're in 8 or 4. It just feels like kind of normal, but there's not as much power, but you don't really need as much power when you're on the freeway anyway, right? However, if one of these fails and it's constantly, let's say it's cylinder number 2, if cylinder number 2 is constantly shut off, when it goes to V8 mode and you're sitting there at idle and stuff like that, it's misfiring. You can feel it's misfiring. I got a truck like that, and they put in coils and spark plugs and injectors. They threw all sorts of stuff at this misfire, and then brought it to me. And within a few moments, I did a compression check, and I was like, huh, there's like no compression on cylinder 2 and 4. Both cylinders are done. Did a little bit more checks. The cylinder wasn't leaking compression though. It just wasn't building it. So I could determine that the valves weren't opening. The valves weren't opening because it had lifters that were stuck in 4-cylinder mode. And so, you know, that's just giving you some perspective as to why you need to know a bit about the cylinder, the variable displacement engines, because they can tend to fail. They're not that reliable. Okay. And then we talk a lot about the material here, saying like blocks and heads commonly manufactured from what?
Lightweight or
Yeah, aluminum. And why do you think? It was in the answer. Why not? Cast iron was the bee's knees back in the day. Lightweight. That means fuel economy. That means lower emissions. So again, if you were to go back 50 years ago, all this stuff was made out of cast iron. Cast iron was durable. It's fairly inexpensive. It was extremely heavy, but cars were big lead sleds and stuff, you know. So now it's like, hey, we want fuel economy, we want emissions. So let's do aluminum. And if aluminum's not light enough or cheap enough, what else should we use? Durable plastic. Did you say plastic? Plastic engine parts. Yeah, that's where we're at. I know. Plastic oil pans, plastic rocker covers, plastic engines, 3D printed. It's going to be great, you know. So, but what's the driving factor? Why are we doing this? Cost is a big one. And fuel economy emissions, fuel economy emissions, fuel economy emissions. Fuel economy emissions are being pushed by the government. The manufacturer's like, all right, fine, we'll do it, but we're not going to lose our profits. We'll do it. We'll use plastic. See, like, so we are running into more and more engine problems. You guys know, you've been seeing some stuff. When I started this job 11 years ago, they were talking about not really doing much with the engine class. Do you know what they said? Our engines don't break, so why do we need an engine class? That's funny, huh? Now, it might not be total huge failures, but you might have something as simple as RTV seal packing is leaking, or, you know, trust me, even though engines are kind of out of style and it's hybrid and EV and mostly EV, engines are still failing, and we don't have a really good way to have the EV do everything we want it to do, like go 500 miles in a day without a $40,000 battery. So like engines are here to stay at least for a while, and they're kind of junky. And you have seen it yourselves. Mm-hmm. Yeah. Yeah, I've heard quite a bit about that. Oh, that one's been around a while. Yeah. Right. So it might just be as simple as the FIPG is, or the RTV is too light and it's a timing cover leak. They might have overdone it and it ends up in the oil pump pickup. I know. So that's the thing. There's job security in this. It's just so my advice to you is learn how to do this, because this is a pretty big percentage of the work that you're actually going to do, and some of the jobs are kind of hard, and you got to know a lot, right? Pistons, aluminum alloys. Sometimes connecting rods are manufactured from powdered materials. This one actually is. This is what they call powder. Actually, this one's not. This one's cast. But I do have a couple examples of powdered rods. It almost looks like, it almost looks like it was like a bunch of dust pressed together and then boom, it was metal. They're pretty interesting. And where they seat up, a lot of times they're fractured. They're doing some wild stuff with the metallurgy. And then if you look into the engine, we're going to talk about bottom end and top end. That's actually kind of where we're going in just a moment. So we talked about the bottom end already, right? Everything below the head gasket, bottom end. Everything above the head gasket, top end. Simply put. Okay, this was a question. Anybody ever heard of replacing a short block? What the heck does that mean? So the block is short, abnormally short. It's below average. What is it? It's the bottom end, but the short block is the rotating assembly. What I mean by that is it's going to have the block, the crankshaft, the rods, the pistons, and it's all already assembled and torqued and ready to go. You know why this is really common? That's the more technical part of the job. So if you're like, oh yeah, let me replace that crankshaft, this is a job at the end of this class you guys will all be able to do. But there's a lot of things that can go wrong. If you have to take this out of the block, now we're worried about all these main journals, which is in the center line, all those main journals. We have to make sure that there's a proper oil clearance here. All these rod journals where the connecting rod's attached, there has to be a proper oil clearance here. There's a lot of torque specs. There's a thrust bearing in this middle journal. There's a whole lot of technical things that go into setting up that bottom end. And then we get into getting the connecting rods and stuff in there and getting these torqued and these bearings. There's quite a bit of stuff to assembling a bottom end. Make sense? And if you think about, they're producing the blocks in this plant and they're machining the blocks. They're producing the crankshafts in this other plant and they're doing multiple lines of assembly. And so this block might be a little different than the block off of this line. And this crankshaft might be a little different than the crankshaft off of this line. So you don't just get to put them together. You got to do some measurements. And then a lot of times they'll come with Toyotas come with typically about 6 different bearing options. And you got to do measurements and select the right bearing to put it in there to have the right oil clearance. There's some stuff that goes into it. You sound like something that you want a bunch of flat rate techs in the dealer doing? No, probably not. Order the short block. It's here. Clean it up, put the head gasket on it, bolt the head on, torque the head. Makes sense? That's pretty common. However, if there's some extenuating circumstances, so for example, one of the last times I was at Penske, for example, I saw somebody had the V6 Tundra that was outside of the recall number. And the factory's like, wait, that one had a failure? That one wasn't supposed to be within the VIN range. So they weren't sure what to do. So they said, tear it down and measure everything. So you guys might have remembered one of the last times I showed up for the previous cohort, there was an engine totally pulled apart, gutted. Henry, you might not have been there quite yet. But there was an engine piece by piece, all gutted, all taken apart. Then Emilio showed up with his truck and put it in the sonic tank because the factory was having them kind of do the research, like put it in the sonic tank and have it totally clean and do these measurements and all these inspections, because they're willing to replace the engine, but they sometimes use some of the more high-end techs to do some more of the research and be like, hey, go about this in a rebuild type of way. Make sense? You can't just be like, oh, no, I don't rebuild engines. I can't rebuild engines. I won't. You can, but you can't consider yourself an MDT. You can't be the master tech, but be like, I can't rebuild an engine. Like, this just doesn't sound right, does it? You know what I mean? So at least know how. I'd say my rule would be everyone has to at least rebuild one engine and have it run and drive it. Maybe not today, maybe the end of the semester, or maybe within the next 5 years. I think everybody should do at least one, even though it's not something you might be doing every day. Okay. My thoughts. What's any, you think so? One all torn down? Yeah. Well, and you see that too. That's actually pretty good input. Yeah, Toyota will put an engine in it. You say it needs an engine, Toyota's like, we'll get it. You tell the insurance company and they're like, well, can't you rebuild it? Because we want to pay for these little bearings. Can we get those bearings? And you'll be like, those bearings, I don't do those bearings. I do a whole engine. I do a short block or a long block. A long block, by the way, is a short block with a head on it, right? So once in a while, it's a customer pay, it's an insurance thing, it's a whatever, and they might ask you to do more than just the basics. So here's your long block. Everything that the short block comes with, plus the head, which will have a head gasket and the bolts will already be torqued and everything. And the head will have been gone through. It may be newer, it may be remanufactured. Got the camshafts, got the timing chains, got the gears, all that stuff. It may or may not come with the front cover. It may or may not come with the oil pan. It may or may not come with a valve cover. It most definitely won't come with an intake and exhaust manifolds. Make sense? But it's basically sealed up. Cool? Uh-huh.
Short and long, pre-assembled.
Yeah, so the short block, the bottom end's pre-assembled and you got to put the head on and then everything else. Long block, the bottom end's already assembled and the head's already on and the head's already torqued and you just got to put on everything else. Pretty much that's it. It's that simple. Then you get into like a full blown, and you can see actually right here, this one's a pretty good one. If it's a short block, you're looking at this and below all assembled, but probably not an oil pan. If it's a long block, it's all that, plus it's got the head, the cams, the rockers, all that stuff should be there. It probably won't have an oil pan and it probably won't have a valve cover, but sometimes they do. But normally if they do, they're probably not going to call it a long block. You know what they'll call it if it comes with the valve cover and the oil pan? A replacement engine. So that's what you get. This thing is done top to bottom, but a replacement engine most likely wouldn't come with manifolds though. They don't really come with manifolds. Now, if you get a used engine, you know what that comes with? A lot of times, everything. And then right there, if you say like, well, hey, it's going to be less work to do a used engine, right? Because you don't have to swap anything over. Well, you've seen how LKQ gets them out, right? They cut, they clip, they cut, they clip, clip, and they cut, and then it's out. So then you're looking at like, oh yeah, I can just bolt this engine in. Then you find one part of the harness was cut off. And then you're like, oh, I gotta swap the harness over. When you go to swap the harness over, you find it runs under the intake, which means you're pulling the intake to pull the harness off, which really means like a junkyard engine ends up pretty much being the same amount of work as like a replacement engine. So we don't really give discounts on those. Now there's some occasions where you could use a lot of the stuff that's on the junkyard engine. And I have done that before. Like I left the fuel rail and the injectors and the coils in, and that did save me time. But this is the thing. If it's a used engine, do you know any of those parts are good? No, especially they've been sitting out in the field in the yard and rolling around and stuff like that and banged into things. So if a customer comes in for, let's say, oil consumption and you find that it's got low compression, you sell them an engine, then you slam a whole junkyard engine in and now it's got a check engine light for a purge valve and a misfire and it's got this one coil's bad. Like then you're going through and you're diagnosing. You think you're going to get paid to diagnose that? They didn't come in with those. You introduced those problems when you slapped that junkyard engine in. Makes sense? So it's always on you. If you're doing a junkyard engine, in a way, one of the best things you can do is pull all the bolt-on stuff off and swap over all the bolt-on stuff from the original engine that you knew worked because you drove the car. Make sense? You put all that stuff on there. I've done it both ways. I've regretted it both ways a couple times. Once in a while I get lucky and I'm like, man, that engine was lower miles and everything worked good. And then once in a while I'm chasing other issues and I find out now I got to pull stuff back off to change the knock sensor because I didn't change it while the engine was out, and that was the problem. Make sense? So you can go both ways. One cool thing about getting a full used engine is when you're done, you got a bunch of used parts. So that's one cool thing is like if I, for the Tundra I got, I did that 2UZ engine replacement, and I saved the starter and the air pump and the check valves and the alternator and the AC compressor, and like I stocked up on a bunch of stuff. So if and when my parts fail, I got some extra stuff. But I did swap over the known good stuff onto the junkyard engine. Cool. So just a little lesson for you as we continue. So let's jump into the block. You guys should recognize some of these parts. Pistons, and these pistons will accept the piston rings. So if you just want to do a basic rebuild, you could re-ring it. You could put new piston rings on old pistons, but the pistons tend to get carboned and stuff. So if you want to reuse pistons, a lot of times you're going to really like hot tank them or sonic clean them and really get them clean. Right? Or sometimes what we'll do, we'll replace piston, rod, and ring assemblies. So back in the day, we had the 2AZ burning a lot of oil, and the fix was to replace these piston with rings, wrist pin, everything, rods, and we'd be bolting those up, and it wasn't a real big deal. But when you do, then you got to determine, are you going to use new rod bearings? Because this is where the connecting rod bearing's at. And the campaign was to replace the piston rings and rod assemblies, but not the bearings, because the issue was oil consumption. And they redesigned the pistons to let well, it's kind of a little bit hard to explain, but I could tell you in this lowest groove where the rings are, where the oil ring is, there's actually holes, and it would scrape the oil and the oil would flow through the little holes. But those holes would get carboned up and then the oil wouldn't really flow through that well. The oil would be left on the cylinder. What would that cause? You'd get oil consumption. That's what the service campaign was for. You have a 2AZ, you have oil consumption, you do the consumption test. If it fails, here's your new piston, rings, and rod assembly. Put those in there and it'll fix it. And so they did tons of them, and that would fix it. Cool. However, if you notice, those pistons and rings and rods, they go up and down in the block. And so the block, for example, should be, I don't know, let's say a round like this. So what if it was, I don't know, we'll make it in inches, right? If it was this way, 4.000 inches. And then if it was this way, it should be what? 4.000 inches. And then the thing is, if it has excessive wear, you'll have a difference between these numbers, and there's a limit to that. Now, it doesn't have to be perfect, but what people would do, they would slam the new pistons and rings and rods in there, and they wouldn't do any of the measurements that the procedure called for. So that's kind of why we're going to go over the full disassembly, the full measurement, the full inspection, and the full reassembly, because you need to know how to do all this stuff, because those engines had out of round conditions like this, like that's a 5 now. It had 5 thousandths out of round. New rings can't seal to a out of round cylinder, right? So if there's a difference between the axial and the radial dimensions, that's called out of round. If I were to draw this as a cartoon, you know what it would look like? What's wrong with that? That's egg-shaped. Anyone for oval? Ovulated? Ovulation? Ovulate? See, out of round. We don't call anything about ovulated. This cylinder is not ovulating, ovulating. None of that type of stuff. It's just out of round. I've seen all sorts of stuff on the worksheets. Circle is ovalizing, oval. Just leave it out. Out of round. You okay? All right. All right, pretty fun. Now there's one more thing. That was just the cylinder from the top. You also got to remember the cylinder looks like this too, right? It goes down like this, correct? So if we have a number here, 4.000, and down here, 4.000, that's good, right? What if this one was 4.005? What do we call that? Conated, conified, conulated, tapered. Tapered's the answer. Got it. That would be a tapered cylinder, right? So again, if we have some of these oil consumption and issues, we have to actually measure the block. So a big part of what we're doing is inspecting the block. The problem with a lot of modern vehicles, you can't machine it. So if the block is no good, basically the engine's no good. Make sense? But if the block is good, you can get pistons and rings. You could get a crankshaft. You could get bearings. But if the block is no good, you need a new block. And if you're going to try to buy a bare block, you're going to look at the price of a bare block, and you're going to look at the price of a short block, and you're going to be like, give me the short block. It just makes sense. Make sense, kind of? Go ahead. Like anything probably above, not anything, but a lot of stuff newer than like a 2010 is probably going to be something you can't bore over. Now a V8, maybe some you can. If it's an aluminum 4-cylinder, I'd consider that more like disposable. Those engines should be good for 200,000 miles. And then when they're burning oil and all that type of stuff, you got 200,000 miles out of this cheap car. Let it go. Just let it go. Just let it go. And what kind of car? What year? Yeah, so if you got 300 out of a Civic, you're pretty good. But like, you don't need to, actually some of those you can do some machining on, but the idea is they're trying to make the car be good for 15 years. They're not trying to have you be driving these cars for 30 years. You know, they don't want you driving these cars for 30 years. Tell the people with the 1998 Camry, it's been recalled, they have to buy a new car now. They've had it too long. All right? It's just not designed for that. You're going to lose that Yaris. All right, that's good. What about if it's cast iron? If you had a block that's cast iron, those are made to be machined over and over and over and over. So, and that's different, and that's fine. It's like, that's like a tractor. Tractors are meant to be rebuilt 100 times, but they're not doing that anymore. Small block Chevys are meant to be rebuilt again and again and again. It's true, but they're different. So then if you look at the block a little bit more, check this out. You guys can see here's the water jackets, water passages. Okay, that's a nice liquid cooled, you know, that's going to be pretty efficient for cooling. You think that's going to be the best for strength? No, probably not. But again, they're not made to have that much power. They're just not designed for that. What do you think about these? What do you want to call that? All right. Anybody have any idea what the cross hatching's all about? Not exactly. The cross hatching is, we got some good guesses. The cross hatching, which by the way, if you look at that angle, they should be kind of like this. Like, what's this? Wakanda forever, like this. All right. Am I right? They cross hatch it like that because if you think about it, you don't want the rings going up and down totally in a dry cylinder, metal to metal, right? Because then your rings are going to scrape the liner, the cylinder. Sometimes I'll call the liner because it does have a lining in it. It's gonna scrape it, right? So we put cross hatching in, and the oil will lay in the scratches, basically. In the low parts of the cross hatching will be oiled, and that will oil the rings going up and down and minimize the wear. So the cross hatching is good. Now, if you have cross hatching all throughout the cylinder, that's a good thing. As your cylinder wears, it wears into the cylinder wall, and the cross hatching is like erased. Make sense? The cross hatching is a scratch, and if it wears deep beneath the deepest part of the scratch is gone, right? So if you look at a cylinder and the cross hatching is gone in some direction, you're like, oh, that one's got wear. So that's just one of the down and dirty tricks. If I looked at this cylinder And they typically wear most on this radial dimension right here. If the cross hatching is gone here and it's gone here, what's that tell me about that cylinder? It is at around. How much though? I don't know. So if I measure it and it's 2,000ths at around and the maximum is 2,000ths, like it's right on the border, we're done. But if it's 1,000th at around and the maximum is 2,000ths, I'd be like, well, I mean, we could bore it to get it perfect, but it's in spec. So I could recross hatch it and run it. I don't have to replace the block or bore the block. Make sense? So the cross hatching tells a story, but the cross hatching is there to really lubricate the pistons going up and down. Cool. And they could be V, they could be iron, they could be aluminum, they could be single overhead cam, single or dual overhead cam, etc. Right? Now when we get into pistons, here's your piston. Why do you think we call this a wrist pin? Yeah, it's just like a wrist, right? That's this. The ASE will not call it a wrist pin. The ASE will call it a piston pin. This is all about a piston pin. Now this piston pin looks like it's pretty easy to change, right? It just presses through the piston into the rod. It depends. This one is a floating design. I know because it has a little circlip right here. If I pop that circlip out, I can push this piston pin out by hand. But a lot of them are press fit, and they can be press fit into the piston, which is a little abnormal. They're more commonly press fit into the rod. So what I mean by press fit is this. If I were to measure that piston pin, right? So now I think I might leave these. I think you guys liked them enough. Gave you a lesson about ovals. If I look at a piston pin right here, and let's make this piston pin a 1.000, that's 1 inch. And it has to be pressed into the rod. If it's a press fit, what do you think the rod diameter, the hole is going to be? Maybe like a 0.99, I don't know, 8 or something. So wait a minute, does a 1 inch pin fit into a 0.998 hole? Well, not without the press, it doesn't. And that's exactly the point. So on those, you press it in and then it's pressed and it's done. You don't need clips. You don't need, to have any sort of retaining circlips or snap rings. Part of the reason I don't love these circlips is because I had bought a Honda Odyssey, not the minivan, but the ATV, the go-kart type thing. And I bought it and it wouldn't run. I diagnosed that it was low compression. When I pulled it apart, the person before me who did the rebuild didn't have that circlip in all the way, and it came out. And what do you think it did? It shredded that cylinder up. It totally shredded it. So like, if this comes out, it totally messes stuff up. If it's press fit, there's nothing that can go wrong like that. Make sense? But here's the negative. If it's press fit and you want to take a piston off the rod, you have to have a special jig and a press tool, and you have to actually press it. Sometimes what they'll do, like when you're pressing it out, you'll use a press, but when you're assembling it, do you want to really like press on a piston you're about to put in an engine? Kind of sketchy. So what they'll do is they'll take the rod and they'll heat the small end of the rod, which is an ASE concept. That's like this end of the rod up here. They'll put that in a press. Now, why would they heat that? So it was 0.998, but once you heat it, it's more like 1.002. And now your pin, you could freeze it if you want and maybe get it to 999, and then you can literally just push it in. With, the rods will be in a rod heating oven, and then you'll set the piston in there and you just be like that. Sound effects for bonus. Then you're done. So you got to just know a little bit about that. Cool. And then here's your upper rod bearing and your lower rod bearing, and here's your rod cap. These cannot be mismatched or anything like that. They have to be in the correct orientation, and they have to be from the correct rod. Those are machined as like an assembly. One thing you learn in engines is you don't, I mean, it works in life too. It's just it's out of style right now. But when things are formed together, it's not real helpful to be swapping and switching, and you've had this part with that part, and then it was with this part. And it's like when you take an engine apart, if it's cylinder 1, I'd mark everything cylinder 1, or I'd lay everything out. 1, boom. 2, if you keep everything where it came from, you're just going to have less issues. Some things you could potentially swap and not have an issue, but a lot of times things that are moving together, they wear together. And when they're worn together, they kind of don't really want to be put in a different spot and been like, this is going to make this work, even though you don't really want to. That engine's not going to last that long, right? These definitely can't be switched. And you're going to see that's a pretty common theme. Then we get into the rings. We got a compression ring, the second compression ring, sometimes they call the wiper. And then the third ring is not for compression at all. What do you think it's for? Scraping what? Yeah, so oil. So as the cylinder wears or as this ring wears, that's one of the reasons you get so much consumption, right? So you lose compression with these rings wearing or the cylinder wearing, and you increase your oil consumption with that third ring wearing. But typically, they kind of wear together. And if you have wear in the cylinder, you're going to get both a loss of compression and oil consumption. Make sense? So if I jump behind a Honda Civic 99, no offense, with 300,000 miles, and they get on the freeway and they punch it, and I see a big cloud of blue smoke, and then the concern is loss of power, like I already got my answer. It does smells familiar. I can smell it from just the story. You guys don't know what it's like with a helmet on a motorcycle. You'd see the smoke. I taste the smoke. I'm like, oh, that's burning oil. So if it's burning oil, and the concern is low power, like it's probably going to have low compression, probably because of cylinder, piston, and ring wear. Make sense? They go together. Cool. And then you can see there are oil return holes right here. And that was the thing that was carboning up on the 2AZ. And they were having oil consumption. And they bored them a little bit larger on the redesign. And that was what was fixing it, at least somewhat. Then, of course, you had some people who were not doing any of the block measurements, and they were putting the pistons and rings in, and then they were still having oil consumption. And then they'd be like, oh, now it needs a short block, though. And Toyota's like, why did you just bill us 20 hours to put pistons and rings in, and now you want to bill us another 15 to put a short block in? Like, why didn't we do the short block the first time? And like, well, we didn't know. And then, you get smarter people like at the region and stuff come in, they're like, what were the cylinder measurements? And they found out everybody's writing the same cylinder measurements over and over because they don't actually know how to measure the cylinders. Make sense? So that's part of the reason that, I'm going to hold you to a high standard, right? And we'll get in there. And then you can see kind of what happens to the ring. Air pressure is going to push it down, get behind it, and help seal it right there. And then when we're on the intake, it's going to push up and push out and help seal it. So they're designed very, very precisely. Pistons get specific rings. You don't just like put these rings on those pistons or whatever. There's specific rings for specific pistons. Cool. And then there's your rod. You can see there's the small end and there's the big end. And this looks like a pretty beefy rod. It looks like this one, some really heavy duty I-beam forged 2JZ super duper big turbo 1400 horsepower thing or something. If you try to put tons of power in, one of the failure points is this rod. You try to push really hard on the piston, and the rod tries to push really hard on the crankshaft, and the rod is like this, like that. You bent a rod. That's what happens when you try to do too much boost. So the rods are one of the failure points. Or sometimes you break pistons too. I mean, you could do all sorts of stuff with performance, but now you can visualize it. See those snap rings? They sketch me out just looking at them. I'm nervous those are going to come out. I'm going to double check that. Cool. And then you can see the crankshaft action. One thing you may not know about the crankshaft is oil is pressurized into the block, and oil is going to be injected into this oil hole, right? And this is cross-drilled to this spot. So how does the number one connecting rod bearing get oiled? Where does it come from? Yeah, it has to go through that passage. So this is a really big thing in the ASE. If you go ahead and you find this bearing is worn and you replace this bearing, but you didn't realize the metal clogged this hole, which is cross-drilled, what's going to happen to the new bearing? Again and again and again, right? So that's some of the concepts. This is the overview, and then, of course, we'll spend a lot of time on the bottom end, too. Cool. So you should at least know, yes, there's no way to get oil out to that rod with pressure unless we send it through the main, because this main sits in the block, right? The main bearings, like where my hands are, they sit in the block. There's no way. How are you going to get oil to that bearing? Oil starts where my hands are at and then gets sent through the metal to that rod bearing. Cool? Yeah. Yep. And then if you look at this, this is a main. You see how it's on center? Main journal, main journal, main journal, main journal, main journal. You see how this connecting rod is off center? That's rod journal 1. Here's rod journal 2, rod journal 3, rod journal 4. Toyota would call this main journal, and they would call this a crank pin, but ASE normally is going to call it a rod journal. Yeah, exactly. The mains and the rods. Now, when we talk about the crank pin, that's the rod journal. If you look at this one, this is called a cross plane crankshaft. This is a cross plane crankshaft. If you look, the mains are in the center line and the rods are offset at 180, right? 12 o'clock, 6 o'clock. It's actually like this: 6, 12, 12, 6. That's a flat plane. It's in a flat plane. Cross plane is like this. This is cross plane. You may have, most 4 cylinders are going to be flat plane because there's 4 cylinders. Once in a while, a 4-cylinder will do a cross plane. That's the Yamaha R1, and they sound pretty good. I'm not gonna lie, but I just don't do Yamaha. It's not my thing. Okay, but they do sound good. I'll admit it. I feel better. Okay, but I'm still not getting one. And then V8s are almost all cross plane, but then once in a while you'll get a flat plane V8, and that's like they had the GT350R Ford. It's a pretty spicy sounding unit. And then they have the Corvette Z06. Those are the V8s that start as a V8 Rumble, but if you listen to them, they scream. They scream like an inline 4-cylinder crotch rocket, and you're like, what the heck is going on there? Well, it depends on how they design it. If you want to design a flat plane V8, you could. It's going to have a totally different frequency than a cross plane, which is the more traditional. And same with a 4-cylinder. You could design a 4-cylinder with the typical flat plane, or you could design it with the cross plane, and you'll be like, that 4-cylinder has like a V8 style rumble. It's kind of interesting. So if you hear my motorcycle is cross plane. You'd be like, that thing's weird. Once in a while, when I'm pulling into Costco, I'll break some old man in New Balance neck. He'll whip like he thinks it's a muscle car, and he'll be like, stand back, like, what the heck? I thought that was a V8. And I'm like, well, it's a V4. And then you're like, you mean it's an inline 4? And I'm like, no, I meant what I said. It's a cross plane V4. That's why it sounds kind of like a V8 if you're not sure what you're really listening to. But also, if they're in New Balance, they get a whole like, that means they're an enthusiast, and they're really shiny white. Am I right? Yeah. Go ahead.
Firing order?
Yes. Oh, yeah. On a cross plane, you have to have pistons firing at the same time. I mean on a flat plane. Right, exactly. Yeah. Correct, because if it's a 4-cylinder, yes. Yeah. It's kind of crazy, huh? Yeah. But you could totally geek out on all that a little bit later. Cool. Now when we're talking about the bottom end, here's your upper and lower bearings. Notice this upper bearing has holes. If you screw up on your rebuild and you accidentally put the holes down here and have no holes up here, you'll block all the oil to all your bearings, and that engine will run for about 2 minutes and 30 seconds and be locked up. You'll have killed it. So just one bearing out of place, done. Okay, so that's the type of stuff we got going on. Now the reason why, look at where those holes are. That goes up into the block. Right here, that goes to the cap. There's no oil coming through the cap. You don't need the cap to have holes in it. You need the block side to have the holes in it. Do not switch them. It's happened. Believe me. Right, and then you can see you got your crankshaft, and your crankshaft may potentially be a little out of balance, or your engine, depending on the frequency and the cylinders and the firing, like when Chevy made the V8 into a V6 and it wasn't balanced real well because it wasn't designed from the ground up. They had to add what we call the balance shaft. And the balance shaft, it actually looks like this. It's real simple. When your engine's out of balance, let's just say it's got a heavy spot, right? When it comes around like this, if the heavy spot is trying to throw upward, what should the balance shaft do? How? By trying to throw down. When your crankshaft is trying to throw this way, what should your balance shaft do? Try to throw that way, right? So the purpose of the balance shaft is just to provide an equal but opposite out of balance effect. And it's kind of crazy, but that's it. Like, to me, I'd rather see it be designed where it doesn't need a balance shaft, but they have their own reasons. I'm in my lane. I don't know sometimes why the engineers do what they do. So that if it needs a balance shaft, that's it. Now, I just explained to you, when the engine throws up, the balance shaft should throw down. That's a pretty fun term, huh? But what if you had it out of time? What if you didn't time your balance shaft right and the engine threw up and the balance shaft also threw up? Now you have a super out of balance. The balance shaft could make it worse. So when we do this, if you look, the balance shaft a lot of times will have sprockets with marks. That's all timing. You have to make sure a balance shaft is in time. It's got to be timed right. Sometimes there's marks, sometimes it's gears, sometimes it's a chain. You know, there's various different designs. But if you see a little chain or something going down to thing that looks like a balance shaft, you need to make sure that's in time. You also need to make sure that the crankshaft and the valves are in time. You understand why, right? If we turn the crankshaft, the piston's going up and down, we need to make sure the valves aren't down when the piston's coming up, because you know what'll happen. Yeah, exactly. Right, so that's when you get into timing. This shows you a little bit of the timing. Cool, just so you can be at least familiar. Now we'll jump in the cylinder head, and again, we'll cover the bottom end again, we'll cover the cylinder head again, but this is an overview so you have the perspective. There will be people starting the rebuilds tomorrow, so you got to know some stuff already, all right? I know it sounds kind of crazy, but all right, here you go. Here's the head. This is the actual housing, if you will. I brought a head over so we could see it. This happens to be a head off of a This is actually a LS head. Pretty confident. So the head is like the bare casting of the aluminum head. You can see it there. But inside of the head, we got a lot going on. If it's a dual overhead cam, we got 2 cams. This head, you'll notice, don't have no cams. You know why? It's a cam and block. This is a push rod engine. So on a push rod engine, we will send the push rods up through these holes and through a rocker arm. The cam's way down there. Makes sense? So this one's a lot more basic. It's a lot more simple. It's kind of old school too in a lot of ways. So, but that's a way to do it. For us, we're more talking about this dual overhead cam, 2 cams, and they're going to lay in these saddles. And so you know right here, there's no bearing there. That cam rides right in the head, or sometimes this will be like the cam tower, we'll call it, or the camshaft subassembly. Some manufacturers do it right on the head, and the problem is if the cam has a problem, like if you run a car out of oil, that's one of the first parts that fails. It'll actually gouge out the saddle where the cam spins, and then your head is shot. Whereas Toyota will use the tower or the subassembly. If that fails, at least you just need a tower or a subassembly. But on the aluminum, they don't put bearings there. So there are no bearings. It's just the cam riding right in those saddles. So, and we could do quite a few checks on those, and we will. And then that's going to sit on the actual head, which is going to sit on the head gasket. Then within the head, you got these spots for the valves. So like this one right here, I'll open and close this valve a few times. You can hear that, right? In fact, I think what I'll do is I'll stop the share for 1 second. Okay, so you can see this valve open and close. Do you think you want this steel valve slapping it up against an aluminum head indefinitely? Think it's going to be happy with that? I don't think so. So what if I pop this valve out, and you'll see it's actually closing up against a hardened insert. We call that the valve seat. Exactly. That's the valve seat. The valve seats on the valve seat. What else would a valve do with its seat? It'd sit on it. Okay, so this has got a worn valve seat. Now, if this valve seat were to be damaged, couldn't you see how it could lose compression through the valve seat? Boom. All right, cool. Now, what about on this side? The valve is going up and down and something's kind of holding it nice and steady and square. It's going up and down and the valve guides the valve, right? So right here, that's a valve guide, if you guys can see that. Oh, you know what? I should have moved. You can see that on the Zoom, right? Don't pin it, just show it to me raw because I want to point to the same thing. It's a lot to keep track of in my mind, a little slow, right? So you guys ever heard of worn valve guides? That's when the valve guide can move loose in there. That tends to have a valve seal leaking oil into there. That's valve guides are mostly like an oil consumption concern. Valve seats are mostly a compression concern. Cool. So those are the main parts of the head. And there could be other parts like the spring, which I do have. You look right here. Here's a valve spring. You guys, what do you think the valve spring does? Give you a clue. Yeah, exactly. The cam makes the valve open. What makes the valve get sucked back closed? The actual spring. Yeah. So if you had worn valve springs, it might not close that fast, especially at higher RPMs. So if we had a vacuum gauge flutter at higher RPMs, it could be weak valve springs. ASE concept freebie for you. Cool. So I'll get back on the share so we can make sure we could see really well. All right. And then you can see there's some other retainers in the valve guide seal and some stuff we'll go into more detail with heads, with the cylinder head. All right, here's the valve train. You know what valve train means? It's how the whole thing moves. Yeah, so we talk about valve train. Remember, we need it to be, what's the name of our boy band again? All right, in sync. We need to keep it in sync. The timing chain is going to be splined to the sprocket on the crankshaft, and then it's going to come up and be splined to the sprockets for the cam or cams, and that keeps them in time. All this here is the valve train. Right here, we've got a shoe. They'll call it a shoe or a guide. Actually, they'll probably call this the guide. Then right here, we have the shoe, which is usually the tensioner shoe, and right here is the actual tensioner. So the tensioner is going to push some pressure on it and keep it tight. What do you think would happen if it got too loose? It would start with a noise, it would slap, and then if it got too loose, it could actually jump time. And then if it jumps time and you have the piston coming up at TDC and you have the intake valve still open, yep. Unless it's a non-interference. So now you just define the difference between interference and non-interference. Non-interference, the piston could be up and the valve could be down and they still won't touch. But remember how I was saying we've increased the compression? Well, as we increase the compression, they've been getting closer and closer together. Most new things are way interference by far, a lot. So if you have a timing chain jump, or if you have, timing belts are mostly gone, but if you had a timing belt break or jump, you're good chance you're going to hit right there. And so if the valves hit, the valves are going to be bent. And if the piston hits the valves, the piston may or may not survive. The valves really tend to not survive. The pistons may or may not. One of the things I do is send a borescope down in there and see if I see any marks on it. So I just had 2 weeks ago, one of my friend who has an AC company who does all my AC stuff. So I get first priority and he gets first priority. Okay. So if my AC breaks that day, like it's happening. But likewise for him, when he's got a car problem, like I'm making it happen even if it's late at night. So he bought it, his Nissan Hyundai. She drove it. All of a sudden, boom, it stopped running. And I was he's trying to have me diagnose it. So I told him, well, take a look at these few things. And he was like, there's some sort of a tooth belt like coming through the front cover. And I was like, oh yeah, the timing belt broke. And he's like, oh, so this thing's done. And I said, well, probably. But if you want to be sure, pull the spark plugs out and send your borescope down in there and send me pictures of what you see. And all the pistons look perfect. If the pistons look perfect with no marks, does it sound like it hit the valves? So I told him, let's hook it up. We'll do a timing belt, tension, or whatever, like a couple $100 in parts. Good to go. Make sense? That one was interference, but it all depends on exactly how much it jumps. Did it jump 5 teeth? Did it jump 30 teeth? Was it at high RPMs? For whatever, that one is definitely interference, but it didn't hit. So once in a while, got lucky is pretty much it. Once in a while, they won't, even if they're interference, they won't hit. The easy way to do it, though, is just get a good borescope and look at the top of the pistons and you know what you got. But some shops are in the old school where they're like, oh, we got to pull the heads off to check it. Pulling the head's a huge job. You know, like why? You send a good camera down in there. We got technology, right? And then if you look at more of the valve train, the valve, a lot of times the retainer, sometimes they'll have a little seat down here, the seal, the spring, the retainer, the keepers. Sometimes right here, there's a little cap, then the rocker arm, and then the lifter, AKA hydraulic lash adjuster. So this one's got quite a few little things going on. In this case, the cam rolls right on the rocker, and the rocker pushes down on the valve, and the lash adjuster just keeps the tension. You don't want it to be too loose, it'll clatter. You don't want it to be too tight, it won't be able to close. Make sense? And we'll get into that when we get into heads. And then right here, you guys should just know the camshaft. If anybody wants to be bilingual, if you want to be able to speak hillbilly, ask me, I know. That there is called a bump stick. It's a stick with a bunch of bumps on it. The bump stick makes it go like that, okay? You notice here's like cylinder one. You may have in a single overhead cam, like a Honda, like a EX, a SOHC single overhead cam. It's got one cam that does intake and exhaust. So you might have like one or two intake lobes, two exhaust lobes for cylinder one. That thing would be lobed up. There'd be lobes all over the place. But more commonly, you do a dual overhead cam. This one, for example, is the intake cam. These two lobes are for cylinder one. These two are for cylinder number 2 and 3 and 4. Make sense? But only exhaust. Cool? And we can get all into those, but for now, we'll keep it simple. This is the lobe. So if you were to look at this, this is the base circle or the base radius. This is like just round. If you measure the distance from the round to the peak, that's the lift. Why is that? That's how far it's open, right? So that's how much it lifts. Then if you measure from the base circle right here, all the way to right here in degrees, not in inches or millimeters, in degrees, if you measure that, that's how long it's open, which is the duration of time it's open. So if you have a valve that opens for just a short duration, but really far, that would be a high lift, low duration cam. Or if you have a valve that opens just a little bit, but it stays open longer, that would be a low lift, high duration cam, right? So there's just different specs, just an overview. Cool. And then you could have, like I was mentioning, you can have a hydraulic lash adjuster, more moving parts, but less maintenance, or you can have a cam over bucket, which is literally just a bucket like this, flat tappet, if you will. Much more simple, but what happens when this valve slaps its way up into the head and this gets too tight? What do you need to do? Either re-shim it or take it out and put in a bucket that's a little thinner, right? So we're doing a lot more. We're doing valve adjustments on this over here. We're not doing valve adjustments on this. Make sense? But which one for a race car? Maybe this one. But which one for a Camry? Definitely this one. Different style. And then there's your timing chain. You guys can see crankshaft down here. The way that timing chains are done, a lot of times it's with colored links. We got a colored link that's going to go to a mark, and we got a colored link to a mark and a colored link to a mark. Timing chains don't need to be set to top dead center most of the time. In fact, a lot of times they don't want you at top dead center, because if you're at top dead center, your piston's all the way up. What might happen as you're rolling the cams over? Right. So a lot of times on an interference with a timing chain, you're not necessarily setting it to top dead center. You're just setting it color to color. Yellow link to the crankshaft dot, orange link to the camshaft dot, orange link to the camshaft dot. Can you do that? That's all I want you to do, okay? That's what it looks like. Literally. These two links will split that line. Now, to be honest, following the service manual can sometimes be a little confusing, but I'll show you and you'll get the hang of this, right? Whereas if it's a timing belt, so you guys can see, if it's a timing belt, there's no marks on the belt. How does that look? Can you see up here too? All right, on the timing belt, a lot of times we have to turn it to top dead center, and there will be some mark, right? Like there will be a mark from here to here, and then there will be a mark up here where we need to maybe line these up. TDC mark, right? So on a belt, we're setting TDC and we're setting the intake, the cam where it should be, and we're putting the belt on, but it's referencing this sprocket to a mark in the block. And it's referencing this sprocket to a mark on the head. And it's always to TDC on a belt. Make sense? Not the case on the cam. Not the case on a chain. The chain itself has colored links. Very common. All right? Because guess what? Some of you are going to be doing timing tomorrow too. You're getting worked. You're going to be. You're going to have to be. You don't have no choice. All right? All right, and then you can see there's that belt. So if you were to look, there would be some mark for the sprocket to the head, and then for the crankshaft to the block. And then a lot of times, I don't really do it this way normally, but a lot of times there's a mark on the harmonic balancer or the crankshaft pulley, and then a mark on the timing cover. And you can get it to top dead center using that mark externally. And you could do that. That's how almost every engine. But the thing is, if you're doing a timing belt, I sometimes will do that step, but a lot of times I'll blow right past that step because there's an external mark, but there's always an internal mark. And I'd rather favor the internal mark because I've seen on a few occasions where the actual harmonic balancer, it's got rubber on there and it actually shifts a little bit. And you could be like, there's no way the sprocket inside can be wrong, but there is a tiny chance that the harmonic balancer could shift and be wrong. So I just don't usually use it, even though 99% of the time it'd be great. But it burned me once and I'll never forget it. All right, then the oil pan, I think you guys got it. You know what oil pan is. You're doing those oil changes and you're loving it. But one critical part, there's this lower part right here. You know what they call this? Down in the bottom? The sump. Yeah, and they may have a baffle on the top. Sometimes they'll call it a windage tray. Does anybody know why? You got the crankshaft spinning up there. You want the oil down. You don't want the oil splashing up and hitting the crankshaft because you guys ever blended something in a blender? Of course, it gets aerated. That's the exact problem right there. If that oil gets aerated, it's kind of foamy, right? What if your brake fluid's aerated? What happens to your pressure? Low pressure, right? If your oil's aerated, low pressure. Did you know if you overfill your engine, your oil will be too high and it'll become aerated. Your oil pressure will not, under any circumstances, ever be too high due to that. It'll be aerated, which will make it too low. Low oil pressure will suck up air and it'll be low. High oil level will suck up air and be low. They're both low pressure problems. Equally bad. Okay, so that's why the oil pan's designed that way. It's to keep the oil down in the sump so that this oil pump pickup can pull all oil and no air and it's not getting foamy and aerated. Okay, that's its job. Cool. And sometimes they're structural cast aluminum and sometimes they're cast aluminum to add rigidity to the aluminum, and then they might just have a stamped steel pan, you know, just for reliability of the drain plug and stuff. Like this one's pretty common. All this aluminum is structural and it's adding to the strength of the block. And then this is just where the oil hangs out. Okay. Sound good? What class are you supposed to be in, mister? For electrical? What time's it start? Okay, give me however much time we got till 5:20. Thank you. Okay, you guys can see. And the cylinder head, typically aluminum. You guys can see where the valves go right there. And where we got the guides. And here's the seat, right? Like what we were looking at on that head. What do you think this whole circle is considered right here? The combustion chamber. That's where the combustion occurs. Exactly. So that's a combustion chamber. Very good. Now this is a 2-valve per cylinder, an intake valve and an exhaust valve, right? On a lot of more modern vehicles, it's going to be 4 valves per cylinder. Better flow. Yamaha does some 5 valves per cylinder, actually. Well, yeah, they do. Just a way to get more air in and more air out, right? All right, and so they do have, they've made a lot of advancements in valves that are going to be better for cooling, going to be better to handle the heat, going to be harder for more durability and all this types of stuff. Like, for example, some of them could be hardened by stellite, right? And that's going to be especially with the stronger the valve spring is, the more that this valve right here is going to slap into the seat. And as it slaps into the seat, it wears the valve in the seat, and then that needs more of an adjustment, right? So they're trying to really make these engines run longer without having to be taken apart to be adjusted and maintained. That's a big push right here. Cool. I think you guys know what the cam is pretty well, right? There's your cam. You can see the lobe. So this is a cam journal. It's like a cam main journal that's round, that rides on the head or the cam tower. Then the lobes obviously have the shape of like the eccentric. It's a lobe. Cool. Old cars had the cam in the block. All right. Old school. We used push rods. I'd love to say we don't need to know that, but guess what's on the ASE? A little bit of that. A little bit of that. Then we moved the cam to the head, and it was overhead cam, right? So you got cam in block right here. The cam was literally just above the crankshaft. And then you had push rods coming up. And then right here, you've got the cam that's overhead riding on the rocker arms and pushing the valves down. It's really not a super big deal. Everything we're going to touch is going to be pretty much overhead cam. Does Toyota make a cam in block? Wait till you see the TRD NASCAR engine. It looks just like a small block Chevy. It does. They do one cam in block. They do only on the race car engine. And that's because that's the rules of NASCAR, which are based in the 50s. In a small block Chevy. Right? I think for valves, you guys are probably decent. Right? Intake and exhaust valves, you got a couple sets. There you go. What are these things called? Nope. They're keepers, yes. And when the keepers go flying, you go crying. And when the keeper goes flying, you need to find that one. Because if it goes in the head and it falls down, it's going to get messed up and stuff. So just know this is going to be the most frustrating part of valves for you. Trust me. All right. And you guys understand the intake and exhaust valves, they control the airflow. They control the intake. They control the exhaust. All right. One point you have to know, when the valve goes down into the cylinder, especially the exhaust valve, it gets really hot, right? Because the exhaust is coming out. Then it closes. When it closes, that valve makes contact with the head. That's the only time it's cooled, okay? So if the valve closes, it passes heat from the valve into the cylinder head. The cylinder head passes it into the coolant, it leaves. Make sense? The amount of time that it's closed for is really important. So when you start doing the big cams and all that stuff, it can tend to overheat the valves potentially. That's why they want to sell you like a whole package, this cam and these springs and these valves and all this stuff, because you're now holding it open longer and further potentially, and the valves have a different weight and the spring has to control the weight. And so there's a lot that goes into it. One of the main points is, what if you had a valve adjustment that was bad and the valve wasn't able to close all the way, it was held open a little bit? It wouldn't cool. What could happen to valves? Anybody know? Valves can stick, but if it doesn't cool, what happens? It's another term. Another term. Valves get hot. And what happens when you get wood really hot? Burns. Valves can burn. If you have a burnt valve, it's probably not because the valve was defective. It's probably because the adjustment was too tight and it wasn't able to close and cool into the head, okay? So if your valve adjustment is too tight, it's going to potentially cause burn valves. ASE concept. Cool. And that's part of the reason we do the valve adjustment, we reshim it. So you know the valve doesn't get more loose at the cam. The valve beats its way into the head and this gets tight and then it starts to get held open and then it burns the valve. That's the normal. Scavenging, who can define this for me? There's a whole big paragraph here, but what is it? I mentioned it once. Remember when we leave the intake and the exhaust open for a second together? The exhaust leaving can make a negative pressure. It can help draw the intake in. We're scavenging power now. We're scavenging as much as we can, trying to get any increase in volumetric efficiency we could possibly get. Cool. It's a pretty neat one. All right. And that's going over scavenging a bit. Now we got a lot of different ways valve can be arranged. Here we got valves that are in the block. So this is an old Briggs & Stratton lawnmower. The valves were in the block. Air would come in, this valve would open, it would go in here, do the Bernie burn thing in the lawnmower, and then this exhaust valve would open and it would leave. I got actually a pretty cool slow motion video I got from a guy on the internet showing the running of this lawnmower engine with a clear head on it and a really fast camera. Pretty cool. You can see it's pretty wild. And then as we get into the valve train, like we talked about, I can explain more with the picture. This is your rocker arm. This rocker arm is mounted on a stud. The rocker arm is going to take the push rod movement right here and transfer it to pushing down movement on the valve itself. Okay, so the rocker arm is like a seesaw on the playground. It just rocks. All right. And then this right here is a roller lifter. Roller lifters are nice because it's rolling across the cam. This one is called a flat tappet or like a solid lifter. This one is going to slide across the cam. Do you think that might come with some challenges? If this slides across the cam? It could, and that's the thing is like when it's old engines and they have flat tappets like that, they have lower oil change intervals, and they a lot of times will also call for zinc in the oil because that's what's going to lubricate that metal to metal better. Right, so we've mostly gone away from any of the flat tappet stuff. That's more race car stuff. We've mostly gone to roller. That's going to be better for maintenance. However, I mean, the flat tappets it's less rotating mass. You know, it was a good thing. It's less things to turn, less moving parts, but not real good when you got a 7,500 mile oil change interval. So kiss those goodbye. And they got lots of rocker arm details. I think overall, if you understand, a rocker arm has to have, depending on where the pivot point is, it can have a different ratio, right? So for what we're doing, you don't need to know. But if you hear this, oh, my rocker arms have a 1.5 or a 1.6 or a 1.7, all that means is if your cam is going to push your push rod up, let's say it would never go this far. Let's say 1 inch. How much is it going to push the valve down? If it's a 1.5, it's 1 inch up. It's going to push the valve 1.5 inches down. What if you had a 1.7? You push 1 inch up, it's going to push it 1.7 down, right? So it all has to do with where the fulcrum is on the lever of the rocker arm. Not an ASE concept, FYI. Just race car stuff. Here's adjusting valves. You guys ever seen this? That Honda. That's definitely Honda. You could loosen the lock nut and then adjust the adjuster screw, and that would tighten this up or loosen it up. Old school Honda stuff is fine. It's legit. This style is actually going to be a hydraulic rocker, most likely. But even these ones, you still have to tighten that up to a spec. Like old school, you'd actually start the car, and while it's running, it would be clattering loud, and you just tighten it up to the clattering starts. Or following the service information, you move the push rod up and down. If it's loose, you tighten it until there's no more looseness. Then you turn it like a half a turn. You follow service info. It's just different styles. If it's this style, this flat tappet, how do you adjust this? Right. This doesn't have a shim. Sometimes they have a shim over, sometimes under. This, you have to change this bucket. Or the machine shop can cut the valve, which is part of the reason we sent it to machine shop. All right. Let me, yeah, I mean, we're still doing pretty good. You guys would be worn out, but that's normal. All right, valve clearance. If it's too loose, what do you expect? If your valve clearance is supposed to be 0.00, how about like a 9, but you actually have a 0.013, what do you expect? It's loose, right? Ticky, 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 ticky. I agree. Ticky, 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 ticky. So if you hear a car, it's ticky, 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 it could be loose valve clearance. What's the problem if it's too tight, though? It's supposed to be 9 and you have a 3. It could. As the valve gets hot, it expands, and that 3,000ths cold may turn into like a -1 hot, which means the valve is never actually sitting up against the seat. It's never cooling. It's going to burn. Exactly. So you go too loose, you get ticky, ticky, ticky. You go too tight and you get burny, burny, burny. So you don't. You got to have it in the range, right? It could be shims. It could be that adjustment like the Honda. It could be replaceable buckets. They vary. All right. And then, and some of the hydraulic lash adjuster ones, there is no adjustment. There is none. Now, you've seen these marks before, right? What was that? Yeah, timing marks. Sometimes they'll call it valve timing, but it's really cam timing if you think about it. What about, I mean, wouldn't it be kind of cool if we could advance that? Or what do we do when it's a little bit behind schedule? You call that something. That's offensive. Yeah, but it's retarded. Advanced timing or retard the timing. It's just the way it is. I didn't make it. Just wait until we cover manual transmissions with clutches. You're going to have a fit with this. Okay, so if you want to advance it, you can, but if you advance it a tooth, you only want it advanced under high RPMs, right? You'd actually want a little bit retarded at idle. What if you could do it on the fly? Would that be cool or what? All right, so now then you're into variable valve timing, but for now, we're just talking about regular timing. This one's actually off. If you look at this, if you go straight up with this, that one looks like it's off a tooth to me. I think so. Well, if you look at this, yeah, maybe it's on. Maybe it's on. Well, that's the point. You guys are going to run into this when you're working on the car. So if you're not sure, you could always jump it over a tooth and see what a full tooth off looks like. It's going to be more than you think. It's going to be like, it's not going to be off millimeters. If it's a full tooth off, it's either a full tooth off or it's pretty much on minus millimeters, or it's a full tooth off. Make sense? It won't be that hard. It could be chain, belt, either way. And some of them are even gear to gear. Gear to gear is really cool. It's really reliable, but it's a little more expensive and it's kind of loud. And so we're not going to do that on a normal car, but like on some diesels or some race cars, they'll just do gear to gear timing, right? Pretty normal. So if you consider the valve timing, it all has to do with when the intake valve opens and when the exhaust valve opens. Everybody clear on that? So if you were to have a little advanced, your intake valve opens a little soon and your exhaust valve, and then it closes a little soon, and your exhaust would open a little soon and it would close a little soon. When do you think you might want to have that a little earlier than scheduled? Higher RPM. Now you guys starting to see how we'd make some improvements with this variable valve timing. Now you see why variable valve timing is going to come in, and we will, right? So if you look, here's how we could change that. We can use our ECM, which will reference our camshaft position sensors, and it'll reference our RPM, and it'll reference a bunch of other inputs that the computer sees. Like, for example, you don't get variable valve timing if the engine's cold. They just keep it fixed. Once your engine's up to operating temp, the coolant temperature sensor sends that signal. Your ECM, PCM, whatever it is going to say, oh, yep, I know exactly where my cam is. I think we should advance it another 5 degrees. It'll actually open a solenoid. The oil will build up in this phaser and actually twist it and force your cam lobes all to be 5 degrees advanced. And that would be really good for high RPM. And you're going to get better fuel economy and you're going to get better horsepower and you're going to have lower emissions. Pretty cool. So we can actually do not only ignition timing be adjustable, we can have the cam timing be adjustable as well through the use of VVT. And these are the passages I was showing you. If we pump oil behind this, it'll advance it to the right. If we pump oil in front of it, it'll retard it to the left. It's the way it is. Cool. So we're controlling it with oil though, and we're controlling the oil with a solenoid, and the solenoid is being controlled by the ECU. Okay, makes sense? You think we could have any failures in there? Especially if we don't have oil changes on maintenance. That's one of the first things is you might get crankshaft, camshaft correlation or variable valve timing codes. And you're like, what's up with the timing? And then come to find out it's because they haven't done their oil change and the oil's sludgy and they have low oil pressure and the oil level's low and whatever. That's going to affect the VVT. Cool. On a dual overhead cam, we're going to do a lot of times VVT on the intake and VVT on the exhaust. And Toyota, way back in the day, there was VVT on the intake, there's nothing on the exhaust. And then when they put the VVT on the exhaust, they called it VVT-I with intelligence. And it was kind of silly, but now pretty much everything's intake and exhaust. And you know the solenoid we talked about? That's the solenoid. So this controls the oil going to the VVT. You can even visually see it. I mean, it's pretty apparent what it's doing. But we got to have a couple wires, and we're going to control that with duty cycle or pulse width. Right? And then you can see we got this is a single overhead. Actually, that's a dual overhead cam. If you look, there's two cams there, but it's one sprocket is going to drive both of those. So that's a timing belt. And this is a timing chain, both overhead cam. Cool. Like I said, there's some gear to gear, kind of old school. You know what happens if a chain or belt breaks? Interference, maybe done. Maybe you get lucky. Non-interference, you pull over to the side of the road and you put a new timing belt on and you're good to go. Cool. But to be honest, a broken timing belt is the death to a lot of engines. So the timing belt needs to be done on a maintenance. And if the timing belt is not done on a maintenance and it breaks, we need to get into a lot of this deep diagnosis and determine if the engine's salvageable or not. And if it's not, it's done. And if it is, maybe we fix it. Make sense? Same thing for a chain, but chains don't have a maintenance interval. So it doesn't say replace your timing chain at 120,000 miles. However, if your timing chain is making noise or has some sort of evidence and you know it's a timing chain issue, then yeah, you could for sure, but it's never called for in the maintenance manual. Let's say that you went in the engine and you were going to do a rebuild. What should you do with the chain? Replace it, yes, but you don't go in just because it hit this many miles. You go in if there's a problem, or you go in if you're doing a rebuild, of course, do the chain and the sprockets, because the chain and the sprockets wear together. But we don't go in there like as a maintenance. But if the chain breaks, yeah, that's really, if the chain actually breaks, that engine's going to have a pretty slim chance of not being really messed up. Yeah. The belt doesn't really mess that much up other than the pistons maybe hit the valves. When a chain breaks, a lot of time that chain rips around and breaks parts of the case off and the cover. They're really a mess. All right. Then we talked about push rods, right? You guys feel like you kind of understand those? Push rod engines, cam in the block, overhead cam. That's when we've got the cams on top. Push rod engine, little tiny timing chain. You see this right here? Push rod engine. This is the crank on the bottom. This is the cam on the top. That's it. This is the whole timing chain right here. They don't a lot of times even have a tensioner. They might just have a little plastic guide. That's it. But when you try to put the cams up in the top, now you got a chain that's got to go all the way up there. Right? So they're a little more complex to do overhead cam. Cool. I think you guys got the intake manifold. We talked about that a little, right? Intake manifold takes the air in the one throttle body and splits it up to the cylinders. And then the newer style intake manifolds may even have a runner on there where you can adjust the length. Right? So here's an aluminum. Here's a plastic. That's a two-piece. But on some of them, like this is too old, they'll actually have a short path or a long path. The long path is good for torque. The short path is good for high RPM power. So it'll be like, hey, long path. And then when you get up to 3,000 RPM, there'll be an actual intake manifold actuator and it'll boonk and give it the short path. Okay, you guys maybe have seen those on the side. They're on a lot of the plastic intakes. Cool. But other than that, it's not real complicated. And then exhaust manifolds, you guys know what that is. Here's one. The O2 sensor's right in there. New stuff is going to have a cat built into it. This was a little bit more old school. Now a lot of times we're having them look a little bit more like headers. This one has EGR pipe going to it, and the cat's up close to the head, which means it's probably pretty new. Newer vehicles have that, right? And again, the manifold's going to take the multiple cylinders and bring it into one so we can run it through a cat. And we prefer to have those cast iron because they take a lot more heat and they're reliable. But sometimes you do it like a tubular thinner steel. It's okay. All right, now we're off of the overall engine, and this is more on the service, okay? So we can roll through this. It won't be that bad. All right, gaskets and seals. What's the difference? Okay. Gasket, gasket, gasket. Fixed parts. Valve cover, gasket. Oil pan, gasket. Front timing cover, gasket, right? These are fixed parts that seal together. Now, what if the crankshaft spins? Spins. Roxanne, you see that drawer right to your right? Open that up. There's a plate in there. I want you to grab it. Looks like a weird shaped plate with a big seal. Will you guys throw that thing up here? All right, so if the crankshaft is spinning, it's got a seal against something. Here's an example. This is a rear main seal. It's a seal because the crankshaft is spinning right here, right? Rear main seal, front seal, camshaft seals. There's only a handful of seals on the engine. Where this plate bolts to the back of the block, gasket. Okay, gaskets and seals are different. You could call it a seal. A lot of people will, but you're wrong. It's just the way it is. Take it from the book and from the Toyota handbook. They're saying it's a seal if it's a moving part. Okay. Here's how we change seals. A lot of times we have drivers. Yeah, I know you can hit them in a circle. You could use a socket and stuff, but you can mess them up. So they do a lot of times have an SST. When you're doing a job, if it calls for an SST, ask me if we have it. And if I tell you, we're not going to do it like that, let me show you how we're going to do it. That's pretty normal in the shop. We don't use every SST that TIS calls for. If you have to have every special service tool every service manual has, you're never going to really be able to fix any cars. You're just going to collect SSTs for one-time jobs. So there's ways to do it, but this is a nice SST actually. But we got to weigh it out. And then if you get into the gasket stuff, it could be a gasket or it could be your favorite, a form in place gasket. Form in place gasket. Form in FIPG. Yeah. RTV is like room temperature vulcanizing. That's kind of a weird term. Some people will call it silicone. It could be silicone, but silicone is silicone. Silicone, all silicone is a type of RTV, but not all RTV is actually silicone based. You see what I'm saying? So like you want to look up what it calls for and use what it calls for. Now, FIPG has oil and it has coolant. There's two different types of FIPG. Okay, they are. But aftermarket like Permatex makes two different types of FIPG too. Some FIPG is black, some FIPG is gray. It'll call out what it's asking for in the service manual, okay? Look at it right there. For coolant application, 1282B. For oil, 295-0103. Cool, a little different. Then right here, it's going to call out how thick the bead should be, where it should be. Should it be inside the hole, outside the hole? If it says 2 millimeter, 4 millimeter, 7 millimeter, we've seen it 10 millimeter. You don't, more is not better. More ends up in the oil pump pickup on the 86. Less ends up, oh, I just did that and it's leaking again, right? It calls for an amount. And prep is key, and you got to have brake clean this. You can't have oil on there. If this FIPG is over top of oil and you bolt it up, the FIPG slides out and you have a huge leak. Don't ask me how I know. A lot of good prep work, but again, you're following the manufacturer service info, okay? And then when we're checking stuff for cracks, we'll get into dye penetrant. When we try to check things for cracks, there's a way we can do it, and then there's sending it out to the machine shop. We may do either or both. When we're looking for oil clearance, we're going to use something called plastic gauge. All I want you right now is familiar with these things. So when you go to put a crankshaft in and it calls for measure with plastic gauge, you come to me and you're like, hey, I need plastic gauge. You should have an idea what you're asking me for. It's going to look like this. It's not the paper though. You don't put the whole paper in there. I've seen it done. You open the paper up and you take this little string out it's like a gummy, it looks like floss. And when you run the cap down, it's going to smush it. It's like a smear. And if it's tight, it's going to be a wider smear. And if it's loose, it's going to be a smaller smear. All right. But if I see somebody put the whole entire paper underneath the main bearing again, I'm going to lose it again. Okay. But I've seen it. All right. So this is the type of stuff you're going to do. We might have to do some thread repair. There's different types of taps. Just so you know, if you're just trying to clean a hole out, I recommend that you use a chaser. All right. When we do some measurement, you may use a vernier caliper. You know how I'm going to make sure you guys know how to use some of these tools? The e-learning. The e-learning is a good one. I assigned the e-learning, right? So we're going to roll through these. We got calipers. We could go over how to read it, but not part of this presentation for now, okay? We've got micrometers, and I could do a separate thing on how to read the micrometers, okay? We've got digital, we got inside diameter gauges, so that's a T gauge. Here's a small hole gauge, just so you're familiar. This, for example, you could use for piston, for cylinder bore. These would be more for valve guide measurements, okay? Dial indicator could be used for out around for run out, but we're not using it that much for run out. We'd more use it for clearances. End play is exactly right, like a connecting rod end play. And then when we go to do these engine removals, there's a few things you must know. Be careful of the paint, be careful of the windshield. If the hood has to come up, we got to find a good place to put the hood. A scratch on a panel is $1,000, okay? So one little scratch on your car, your hoopty thing is like you cry a little bit and then you're over it because there's already 10 more. But on a customer car, a scratch on a panel is $1,000 minimum. Minimum, right? No scratches while we're doing this work. So we got to be really careful about it. Organization is going to be key. We're going to go over how we're going to organize it, how you're going to label stuff, how you're going to know where the harness goes. Pictures has become really, you could be successful with pictures. There's some diagrams. When we go to do the work, there's a procedure to depressurize the fuel system. I'm not going to tell you exactly what it is. I know, but I want you to be following service info and referencing the steps. Sometimes they tell you to do dumb stuff. Sometimes they tell you to pull the engine, drain the transmission fluid. Don't do dumb stuff, but reference it. Is Andy here? No, he said. Is Andy here right now or no? Andy. He's assigned to this room. That's all right. Let him do his thing over there. That's even better. Oh, good. So the student was just confused. Even better. Good job on the engines. We're all good. We'll take care of it. I saw it. All right. What if you guys want to drain the coolant? Have you drained coolant before? Yeah. Yeah. Right on the radiator, right? That's a good way. All right. The engine's still pretty full. Did you know some engines actually have a drain? So, you know, if you're going to pull an engine, you're going to want to get as much coolant out of the engine as you can, because once the engine's swinging around on the chain, it's spilling here, it's spilling there, and you're walking through it. Try to get it as empty as you can, just to keep it as clean as you can. When we're done pulling engines, we'll be pressure washing. We can't be leaving a mess, okay? So you're going to spend the time prepping it, or you're going to spend the time cleaning it up. When you're cleaning it up and it's 9:45, you're going to be cranky. So do it on the prep side. Same with hood. Notice right here, you can make some marks. I find you don't even need to. You can usually see the marks on the paint, but when you go to put the hood back on, you're all not body techs, but there's some tricks to get that hood pretty well aligned. It needs to have even fender gaps and close nice and clean. Josh, you got some tricks, huh? On some, maybe yes, but I don't know about on all. But it sounds like on the Tundras, maybe yes. Yeah. Sometimes they don't always sit just right, but it's just something to keep in mind overall is when you bolt this back up, you can run the bolts in, but you got to actually make sure the alignment's good, because that's the type of stuff the customer sees. Customer doesn't know if you put a torque wrench on every bolt. Customer knows their hood looks crooked and it doesn't close right. So don't miss those little details. And if you need engine hangers, we have some. A lot of times they come with some and sometimes they don't. Okay, and then when we're lifting, again, there's a little bit of stuff we'll have to cover about like how to be safe, how to make sure the chain is correctly rated. making sure that the crane is correctly rated. Hey man, you're across the way. Roxanne, tell him where he's at. You're looking for Mr. Fu, right? Across the way. We found out wrong class. You'll find him. Okay, so when we go to do this, we got to make sure the chain is rated for the right weight. How much does the engine weigh? I don't know. Depends on which engine it is. So if it's a V8, it's going to be like if it's a 3UR, that thing's a beast. But if it's a A25, it's a little tiny beast, right? So making sure our stuff is right. And we did have an issue with this is a stand, but we had a crane where one of these pins was out of the wheels and I didn't catch it and the students didn't catch it. And it went like this. And there were a lot of people who saw it and it was kind of a big deal. And so I realized on day one, this is day one, I need to make sure you guys all understand, look the equipment over. If there's a bolt that fell out, if there's a pin that's out of it and stuff, just be like, hey, something's wrong here. For here and for work both. Because you're going to work with some ding-dongs just like I work with some ding-dongs. I know who used that crane last. And I was kind of like tempted to turn around and be like, hey, but you know what? That's not a good example because it's my responsibility to make sure the pins are in and the bolts are in and the stuff is safe. Okay, so I just took, it was my engine that got dropped and it broke a couple things too. So I was kind of frustrated. And it was like, and I was not teaching my own class. I was subbing for a different class, you know, last minute, no prep, like type of thing. And you get what I'm saying? Don't waste the time trying to blame somebody. Hey, you didn't put the pin back in. Like stop before the engine falls and then go figure it out. Okay. So I'm charging all of you with that. Nobody can be like, hey, I pinched my finger because somebody else didn't do it. Like you're responsible for you. Okay. And then we do the disassembly. The biggest thing I want you to know is you have to have a way to remember where stuff goes. So sometimes if it's a cover, people will make a cardboard cutout and poke the bolts back in the cutout so they know. Some of these covers, like on a 3UR, have 4 different bolt sizes in one cover. And if you put the long bolt in, it won't go all the way in. If you put the short bolt in, it won't actually grab enough. And if you try to put the long bolt in and you keep trying on it, you'll actually break the bolt or break the housing. So like you're trying to do all this while that FIPG is curing. And the general rule of thumb is 15 minutes from when you put the FIPG on to torqued. Okay, so you don't have time to be disorganized and be like, oh, let me go get this other thing. Because every minute that FIPG is starting to cure, and if oil gets behind it, it won't seal right there. So this is all about, it's not about working really fast and making the wrenches turn really fast. It's like having your mind organized, having it clean. You might consider turning the music down a little bit and having your workspace cleaned up and organized, or otherwise you're kind of frantic and you're screwing stuff up. And then I'm here helping you at 11:45 at night, and I'm gonna hear it when I get home. And this is all firsthand experience. So I'm trying to warn you, like, keep it clean and organized, and everything will go pretty well. And a big thing that I like to do when I take an engine apart, if it's a big part, do you know where the timing cover goes? It's not that hard to figure it out, right? You don't need it sitting up on your bench. Take the timing cover and you can put it beneath. Now, where you need things is like when you lay the rods out. Keep your bench space open for your important things. You don't need an oil pan taking up a big part of your bench. You know where the oil pan goes, right? You know where the timing cover goes. But for the smaller parts, I like to keep them organized. And I generally like to do, if I pull it off, I start in the left and I go from left to right. When I put it back together, guess what I'm gonna do? I'm gonna go from right to left, right? Minus the bigger parts, which, like you're not gonna put the engine in without the oil pan on it, right? You don't need the oil pan to be in line. Just put the oil pan somewhere where it's out of the way. Okay, these are my advices. You can also use Sharpie, tape, parts trace, organization stuff. You can bring stuff in if you want, pictures, whatever. But that part I don't micromanage. But if you ask me for help, this is my protocol, not just with this class, okay? If you ask me for help, you have to take my advice, okay? If you don't want my advice, no problem. Don't ask me for help. Make sense? So my job is here to help you. But if you want my help and you got a big old pigsty over here and I got to trudge through all the coolant and the bolts are here and everything is over there and stuff like that, I'm going to help you. I'll trash all these shirts. I'll roll around in the dirt and everything. But you're going to get some correction too. You'll be like, hey, you can't be working like this and having me come try to work in no kind of pigsty. Okay? So be nice. All right, you guys got any questions? Do you feel like you get the gist of things? Good, we got some things to do. So let me pause that.